Calculus, video 55, linear approximation. Okay, so in linear approximation, what we're doing is we are approximating the y value of a point on a curve using a tangent line. And I think I can probably describe that a little bit better with a picture. So here I have a function, the curve there in blue, f, and I want to find, or at least want to approximate, the y value at some point x. In other words, I want to approximate this point x f of x. What is the y value at x? We'll call this x f of x. Right? Maybe it's not so important that I know exactly what the y value is at x, that I know exactly what f of x is. Maybe it's okay that as long as I get close, it's fine, as long as we can approximate it. All right, here's how we're going to do that. Suppose we know what happens at a point a f of a. So a little bit, say over here. Here's an x value of a, some point that I know, and I know the y value at f of a. Maybe it's an easier y value. Maybe a is like a nice constant, and x is like some weird decimal, right? And so we know what happens at a f of a, and I would like to approximate what the y value will be for x. What is f of x? One way we can do this is to take what we call a linear approximation. So what we're going to do is we're going to take the tangent line at a f of a. Something kind of like that. Nice tangent line at a f of a. And we're going to use the value of the tangent line at x to approximate the f of x on the curve. In other words, at x, what is the y value on the tangent line right here? Let's call our tangent line L of x for a line. So what I'm looking for is what is the value of L of x of my line at this particular value x here. Notice that the value of the line at x is pretty close to the value of the curve at x, with an error being about, say, this much right here. This much would be error. Again, we're using the value of x on the line to approximate the value of x on some curve. And maybe what you're imagining here is we have a really complicated curve. We're not going to really have complicated curves in Calc 1, but let's suppose we have a really complicated curve, and we just need to be able to estimate what happens on that curve at a particular x value. One way we can do that is, if all we need is an approximation, is we could use a line, because the line is one of the most basic polynomials we have, and we could plug the value of x into our line to get that top dot in green right here, and use that as an approximation for what the function value is on the curve. That is the idea of linear approximation. And you might be thinking, well, how could we ever use this? Turns out, and I'll show you either in this video or a subsequent video, how important this idea of linear approximation is. All right, so suppose that we know a f of a. So we know over here a f of a, and we want to approximate f of x, the function value at x. We can do that using the line, the linear approximation, the tangent line at a f of a. So L of x is the tangent line at the point a f of a. We use the tangent line at a f of a. We find out what is the equation of that tangent line, evaluate that tangent line L of x at x, and use that as an approximation for f of x, the function value on the curve. Okay, in order to do that, we need to find the equation of the tangent line. I guess before I do that, no, let's go ahead and try that. What is the equation of the tangent line? And what we're trying to do here is find the equation of the tangent line in general, right? I haven't given you what is f. I haven't told you what f of x is yet. I haven't told you what point A is yet. So we're trying to find the equation of a tangent line in general so that we can apply this to any curve at any point A. Okay, well, the equation of the line, you could either go with y equals mx plus b, or y minus y1 is equal to m times x minus x1. I think I'll do that, the point slope method. So equation of a line, tangent line, all lines can be found by y minus y1 is equal to m times x minus x1. Okay, what we to do to find the equation of the line, you need a point and you need a slope. What is the point and what is the slope? Okay, so the point will be the point of the line that we know. We only know one point on the line, and it is this point at a f of a. So the point that we'll use on the line is a f of a. And what that's representing is the a value here is representing your x1, the f of a is representing your y1. So a f of a, that is like x1. I should probably write it a little better than that. Let me try this again. Let me get in more space. So we have the point is a f of a. It's the point we know something about on the curve. It's also on the tangent line. And that's going to be represented in this equation by x1, y1. And the slope. What we're talking about here is the slope of the tangent line at a f of a. Well, we're in calculus. How do you find the slope of the tangent line at a point? That is the derivative. The slope of the tangent line is the derivative function evaluated at a. Let's plug those values in to our equation of a tangent line, to our equation of a line, y minus y1 is equal to m times x minus x1. And we get the equation of the tangent line. We have y minus y1, the y1 value is f of a, is equal to the slope f prime of a times x minus x1, which is a, x minus a. Okay. Let's go ahead and solve for y. Solving for y, we get y equals f of a, adding f of a to both sides, plus f prime of a times x minus a. And this would be the equation of the tangent line at a f of a. Okay. We're going to call that the L of x, the equation of our tangent line. Instead of y equals, we're going to call it L of x equals. So the equation of the tangent line is L of x is equal to f of a plus f prime of a times x minus a. That is the equation in general of a tangent line at the point a f of a. And we can use this. We can use this equation of a tangent line at a f of a to approximate, spell it right, to approximate the function value at x. All right, so pick any x that's not a, and we can approximate the value of the curve at x. We can approximate f of x using the equation of this tangent line. Again, picture here is we know a f of a. We can find the equation of the tangent line, the line in green there, at a f of a. We can use that, plugging in x into that line gives us the dot, the function value L of x up here. And we'll use that as an estimate of the function value on the blue curve. That is linear approximation. Okay, let's try an example. Maybe work it out through an example is sometimes useful. So, example. Use linear approximation to approximate the sine of 0.4. We'll stop there. We'll just add in the rest of the stuff later. Use linear approximation to approximate the sine of 0.4. So we're talking about an angle of 0.4 in radians. We'd like to know what is the sine of that angle, but we're going to use linear approximation to do so. Okay, so step one. First, let's choose a value of a that we know. So our value of a has to be somewhat close to 0.4. We can't get too far away from it. Go back up to the curve. And what we're saying here is the a and the x value have to be pretty close. The x here is the 0.4. All right, that's the value of the function. That's the x value that I would like to know the function of, the sine of 0.4. So the x is acting like 0.4 in this case. The curve in blue, my f of x here, is in this case sine of x. That's not the graph of sine of x, but just to kind of understand here. So we need to pick an a that is fairly close to x. It can't be too far away, because if a and x are too far away, what happens is, if your x is, you even just picture it a little bit further down the road here, now the function value at that particular x is here, but keep this line going, right? And the linear approximation is way up here. The further that x gets, the worse your linear approximation is going to be, because the curve is going to more than likely continue to curve away from the line. So all that to say, a and x can't be that far apart. Okay, so let's go back down here. First, choose an a value. Choose an a value near 0.4. And it also, you need to know what the sine of that a value is, such that we know the sine of that particular a value. Okay, well, what a value would you like to choose here? Some number that's close to 0.4 that we know the sine of. Let's make it easier on ourselves. Let's choose a equals 0, okay, because I know the sine of 0. Sine of 0 is just 0. Right, so that's a pretty easy one, right? We can do that. So here's what I have. We know that sine of 0 is 0. I just wrote that down. Therefore, if I plug in 0, an a value of 0, if I plug in a value of 0, I get out a function value at a of also 0. That is my point. That is the point that I'll need for my linear approximation. 2. Once I know that, I want to use that linear approximation. You need to know this formula. F of a plus f prime of a times x minus a to approximate the sine of 0.4. In other words, the function we're talking about is the sine of x. And what I'm looking for is, what is f of 0.4? What is the sine of 0.4? That's what I'm trying to find out. Well, not actually find out, that's what I'm trying to approximate. Okay. In order to do that, I want to use this function here. Now I know my a value is 0. I know my f of a value also 0. What I need is the derivative at a. So find f prime of x. Let's call it step 3. Why not? Find f prime of x. Well, if f of x is sine of x, then f prime of x is cosine of x. And then we actually want f prime evaluated at a. What we want here is the slope of the tangent line evaluated at the point a, f of a. So we need f prime of a, not just f prime of x. All right, so f prime of x is cosine of x. F prime of a, that is f prime of 0. That's the cosine of 0, which we know is 1. Okay, so what we're saying here is the slope is 1. This is our slope. Let's go ahead and find our line. So L of x, then, our linear approximation, which is f of a plus f prime of a times x minus a, the more you write that down, the better, is equal to f of a. F of a is 0, right? Back up here. F of a is 0. Plus f prime of a, that's 1, that's the slope, times x minus a, and the a value we chose is 0. So we get this kind of very basic line of our linear approximation is simply just 1 times x, or x. That is our linear approximation function. It's what we're going to use to approximate the sine of 0.4. Okay, let me give you a very rudimentary graph as best as I can do here to try and show you on this particular example of what is happening. Sine of x. Sine of x looks like this. Starts at 0, 0. It goes up, it goes down, it goes up, it goes down. Looks something, I'm sure, can be drawn quite a bit better, but something like this. This is f of x equals sine of x. It goes up to 1, down to -1. Okay, we know it peaks here at pi over 2, goes back to 0 at pi. Here's negative pi over 2, negative pi, so on and so forth. What we want to know is what happens at 0.4, 0.4. Okay, so we're asking ourselves, what is the function value here at 0.4? I'd like to at least approximate the function value at 0.4. That's my x value. And what we're going to say is the best approximation, the best linear approximation that we can get using an a value of 0 is the line y equals x. Right, the line y equals x is just a line that looks something like this. Try that one more time. But what you'll notice is for values close to 0, for x values close to 0, that line is actually a pretty decent approximation of what the curve of y equals sine of x is, of f of x equals sine of x. Let's zoom in just a little bit, because probably more likely what's happening is the sine of x curve is looking like this. The linear approximation is kind of coming more like, that's not very good, more like this, somewhere around there. And at 0.4, the function value at 0.4 is somewhere around here. That's what we're trying to estimate. What we're going to use to estimate that is the value of our line, of our tangent line at 0.4. It'll be a little bit off. We'll get a little bit of error right in here. But again, we're just trying to approximate it. So we're going to use our line to approximate the function value. And the way we do that is this. We take L of x is equal to x, that's our line, and we plug 0.4 into the equation of our line. So that would be plugging 0.4 into x, which is 0.4, and that is the linear approximation of sine of 0.4. In other words, 0.4 is approximately equal to the sine of 0.4. Okay, good. Not perfect, but it's a good linear approximation. You may want to, at this time, take your calculator out and see, well, how close were we, right? We kind of were trying to do this mainly without a calculator. Like, well, what if we didn't have a calculator around? How could I approximate the sine of 0.4? Well, we found by a linear approximation, we could just plug in the value of x, which is 0.4. But how close is that? What we want to do now is, I don't know what step I'm on. Step 4 is determine the error. Okay, it's kind of like, oh, here's your calculator back. Now let's actually find out what the sine of 0.4 is and see how close that linear approximation was. Well, take your calculator, make sure that it's in radians, and find the sine of 0.4, the actual function value at 0.4. So to determine the error, we'll need the actual. The actual value is the sine 0.4, and we find that that is about 0.3894. All right, that's pretty close to 0.4. So what is the error? The error is always your approximation minus your actual. Error is the approximation minus the actual. So our approximation to the sign of 0.4 by our linear approximation was 0.4. The actual was 0.3894. And if you subtract that, you get 0.0106. And that is the error. Honestly, that's pretty close, right? The line as an approximation of the curve sin of x at 0.4 was only off by 0.0106. That's not bad. The follow-up question that might be like, well, relatively speaking, how good is that? Well, we can turn this error into what's called relative error. And what we do by relative error is we take our actual error we divide it by the actual amount. So we take our error, we divide it by the actual amount times 100% to put it into a percent. So we have this. Relative error is our error, 0.0106, divided by the actual amount at sign of 0.4, 0.3894. If we do that, divided by 0.3894, I'm getting 0.02717. I'm going to multiply that by 100 and call it 2.7%. In other words, we have about 2.7% error. 0.0106 is about 2.7% of 0.3894. We have 2.7% error. This is our relative error. And the question is, in possibly a different context that has to do with, some sort of application of this, what is an allowable relative error? Do we need to be within 1%? Do we need to be within 5%? Do we need to be within 0.1%, right? Depending on how close we need to be, we can find something, we can get our A close enough, if you will, to have a relative error that is less than whatever the specified amount is. Okay, very good. Let me do one more thing before we end this lesson. I tried to make a drawing here of sin of x, the curve sin of x, and the lines. I didn't ever label this. This was L of x is equal to x. I went ahead and did this on Desmos, and I think I can paste it in here for you guys to see it. So, graphing this on Desmos, it looks something like this. I switched the colors up, but the red curve here is sin of x. The blue line is y equals x, or L of x equals x. And you'll notice for values close to 0, for our values close to the A value of 0 that we picked, this linear approximation really is a good approximation for the sin of x. But it only lasts for so long, right? 5, 2, 1, these are all 1, spacing by 1 blocks. I don't know that I can zoom in. I can a little bit. So it looks to me like this is only going to be fairly accurate from about, say, negative 0.5 to 0.5. After that, it gets to be quite inaccurate. We wouldn't be able to estimate the sine of 4 with L of x equals 4. I mean, the error would be, I can draw it on here. The error L of x equals 4, it would be up here. The function value at 4 would be down here, and you'll see the error is huge. But as long as we stay within like this negative 0.5 to 0.5 region, that line is a really good approximation for the sin of x. And in fact, later on in math, we'll have this sort of statement here. For x close to 0, sin of x can be approximated with x. And that'll be a valuable thing that we'll use later on.